My presentation will be divided into three sections particularly. First section will be the introduction and the background, and second section will be the power quality control in the microgrid system. And last part of the presentation will be how the microgrid is operated in a off-grid mode as well as in a on-grid mode. That is the seamless transition of a microgrid operation. And under this introduction and background, we'll be discussing few basic concepts regarding the renewable energy sources and microgrid as well as the smart grid concept, and what is the present and future scenario of our country, and also at the globe also, and what is the major importance of power electronics technology when we'll be integrating the renewable energy system, and few design aspects of RES integration also that we'll be discussing how to design a system. Coming to the renewable energy sources, as all of us know, these sources are promising sources for generation of the power at present, because there is a depletion of fossil fuels, as well as you know that there is a environmental effect also. We have to maintain the environment by maintaining the this greenhouse effects of these traditional power systems. Then mainly if you'll see at present, the solar and wind are mainly the renewable sources for power generation. Because this is plentifully available, still it is intermittent in nature depending on the climatic conditions and environmental issues. And to take care of that intermittency in nature of these sources, the energy storage systems are vital components of a microgrid. If you say the energy storage system is much more important in case of a standalone microgrid system. But generally, the energy storage systems are used for a proper operation of the microgrid to maintain the power flow, power quality. All those things are there. There are much more research is going on also. How you will optimize the energy storage devices, and which of the energy storage device is more economical, as well as the lifespan is more, maintenance will be less. All those aspects are there. A lot of research in the energy storage. Similarly, as we told you that when we are penetrating the highest amount of the renewable energy sources to the existing grid, definitely there will be so many issues will arise, like the stability issues, power quality issues, and depending on that, power management also, it is also one of the major aspects. Means how to optimally you can manage the power allocation. All those issues are there that many researchers are doing the lot of work in different research areas. And particularly, as I told you, I will be focusing two aspects where our PhD scholars are working, particularly in the power quality, and another aspect is the seamless operation of microgrid system. These are the various renewable energy sources. All of us know. Will be just overlook all those slides. As I told you, is always we look for the new renewable energy sources that you can also think of. Existing sources are, as all of us know, that wind, solar, ATAL, geothermal, fuel cell, all those things, but still there is a chance to go for the new renewable energy source. And how the power is generated from the wind, that is a schematic picture is given here. As the wind turbine is connected to the generator, and the generator is giving the output as AC. then how you will synchronize with the system. In that way, the power electronics technology comes into picture to maintain the same voltage and frequency of the grid. We have to take the help of a DC to DC converter as well as a DC to AC inverter, because in inverter will maintain the or will control the output voltage as well as the frequency, so that you can synchronize with the utility grid. In that way, the wind power is generated. And PV also the same manner. The PV, we are getting the PV power as the DC output voltage. And here also we are using the same power electronic technology to interface with the utility grid. These are the very basic block diagrams of the PV integration system as well as the wind integration system. Next, we will be coming to the fuel cells. Nowadays, we are also doing some laboratory scale research with the fuel cell, because this is more expensive at this moment. Maybe the in future the cost will be reduced. We can think of that this fuel cell will be using the hydrogen and to get the power. And here the power is also DC. And in the same manner, you can go for the power electronics interfacing converters to interface with the utility grid. Since fuel cells produce DC output voltages, inverters are required for interfacing to the AC system. It is very expensive, as I told you, and you can use it for a central heating power systems. And next we'll be coming to the battery storage. As I told you, the battery is very much important for microgrid system, because the renewable sources are intermittent in nature. In that way, there are different types of the batteries also, lead acid batteries, lithium battery, and nickel batteries. And depending on the type of battery, the rate of charging phenomena as well as the discharging, that also depends. Still, because the battery, when the suddenly the load will be increased or decreased, this battery may not cope immediately. It may take little time. In that way, you have to come to the supercapacitor. Means in some research articles, you will find the supercapacitors are also used along with the batteries, because the supercapacitors can take the important role when there is a sudden change in load. That time, the supercapacitor will come into picture. Once the battery will take up its full charge, or when it will come to the complete operation, that time the supercapacitor may be disconnected. The next is a distributed generation. All of us also know these are the small generating units and mainly connected in the distribution network. And it is at the load center, you can say, distributed network. And they are the subsets of distributed resources. Distributed resources means that is the combination of generators, DG, as well as the energy storage devices. And microgrid also are the electric network utilizing the DR to achieve the independent control from a large widespread power grid. Because these are the isolated grid, you can say, then independent control is possible. In the remote village also, you can go for the microgrid, or a market complex, you can go for the microgrid system that can be used in the standalone mode. If the power is more also, you can go for the grid connected. It is up to the design aspects how the operation is. Because nowadays many means incentives are coming to develop these microgrids in the institute level campus also, so that you can utilize the power at your campus and the surplus power can be fed to the grid also. That is also there. Then this is a general diagram of a grid-tied renewable energy system or microgrid, where there are so many different renewable energy sources are there, and for storage purpose you can use the electric vehicle also, And the interfacing converters are there depending on the source, whether you will go for the DC to DC as well as DC to AC. Two-stage conversion device are there and single stage also device there. That depends on the configuration. Then these are the system components of DG system. All of us know, as I told you, mainly the load will be there. It is different types of load. Now also we are talking about maybe sensitive loads or means static loads, you can say, or dynamic loads. So many types of loads. Depending on that, you have to segregate the load also. Means you can make the clustering of the loads so that importance of the load or the priority based load will be connected to the microgrid. That is during the standalone system or a islanding mode system. And we told you about the power electronics converters, which are the heart of this microgrid system, you can say. Because of these devices, we are able to connect with the utility grid. And energy storage, as I told you, that this is also a vital part to maintain the power flow control as well as reliability of the system. These are the components of the microgrid. And this is also what I told you. Microgrids are independently controlled, small in size, electric networks powered by the local units distributed. These are the very small examples, you can say, where the applications of microgrid or the PV power application or wind power application, all those things are there in the residential purpose, or you can say the data center, or where you can use the in the institute campus or in the industrial belt also. These are the microgrids applications are there. There are so many advantages. As I told you, this is having the independent control and more flexibility will be there. And so many advantages are there. These are the advantages already pointed out. Here, one of the research article, you can say, one of our PhD scholar, he is working in the multi-level inverter for the application of the PV power or for the application of renewable energy sources. Here, if you see, there are different sources and energy storage devices are connected to the DC grid, you can say, DC microgrid. We are maintaining a DC voltage. Here also you can connect directly the DC loads to the DC grid. And that DC grid, again, the DC microgrid, you can say that that is connected to utility grid by means of the multi-level inverter. Because this multi-level inverter is having more advantage compared to the two-level inverters or three-level inverters. Because here the power quality can be easily controlled. You can improve the power quality easily by different control schemes. And this can be used also multi-level inverters for a high level or medium level power rating. That is also one of the advantages. And there are different configurations possible. Nowadays, many research articles you will be finding the different topologies of the multi-level inverter. Now, we are not working with the conventional multi-level inverter now. We are doing the research at the different topology. It means how to reduce the switches. It means a reduced switch multi-level inverters topology. And as I told you, what is the microgrid and smart grid? When you include the information technology along with the microgrid, this will be treated as a smart grid, you can say. Or when you will go for the IoT-based control and information technology together, and it is a very embedded system. Means from information flow is very much important in case of the smart. Because what we are doing at the research level or at the laboratory scale, this is just a preliminary idea how the microgrid is operating at a small scale. But when you go for the complex power system, that means here there is the data information is very much important. And that talks about the smart grid. And as I told you, some backgrounds are there. We have collected few data so that you can see that what is the global scenario of the different renewable energy sources, how the power generation is increasing, and definitely the time to time we are increasing the power generation from the renewable sources. And here also you can see that how the top 6 countries for renewable energy status, you can see here also where India is also in between. But we are also in a good position, and we are expecting that we will be doing uh, better. This is the solar and wind capacity in the world that you can see. And now, what is our current status, or what is the task for the power industries, you can say, or the like the people like us also we can think of, because now the every residential owner is also one of the, you can say, the customer as well as the producer of the power also. In that way, we can say that this is the task for each and every individual also. Currently installed total wind generation capacity is 37.69 gigawatt in the financial year 18-19. And now you can say maximum wind power generation is in western and the southern regions. Okay, that is 90% installed. Target for 22 is 60 gigawatt, which implies almost doubling of the currently installed capacity. That is the target now for the wind power generation. Similarly, you can see here also the currently installed total solar PV generation capacity is 28.18 gigawatt. In the financial year, it is calculated 18-19. Most regions of India have an abundance of source of solar energy. That is true. Target for 22 is 100 gigawatt, which implies almost 3 times of the currently installed capacity. This is the target for all of us, you can say. Not only for power industries, you can think, you can generate at your home also 5 kilowatt, 10 kilowatt power. That is also surplus for the power system. And this data we have collected from MNRE of this. Now you can come to the, as I told you, the power interfacing systems. That is nothing but the power electronics converters. And your input will be the AC power or DC power. Depending on that, you have to select what type of power converters is used so that you can interface with the utility grid. These are the different applications of the different types of converters, you can say, and different switching capacity also it is written. And switches will be there, IGBT, IGCT, all those switches are mostly used nowadays for inverter circuits. This is just a summary kind of thing given. These are the switching devices. Then next come to the PV interfacing inverters. All of us know that inverters means it will convert from DC to AC, and the AC output can be controlled. That means voltage as well as frequency can be controlled. And depending on that, you can interface with the grid. And definitely the question will be that interfacing inverter output is not a pure sinusoidal. And to get the pure sinusoidal, we have to think of the control strategy. How you are designing a control strategy, that is also one of the major aspect in microgrid. And so that you can reduce the filter size of the passive filter. This is a PV system. You can see here the PV array. You are getting the PV, means the output voltage of PV array. That is again given to the MPPT controller to extract the maximum power, and so that you can feed that DC power And this is a boost converter, you can say. The boost converter is mainly to boost the voltage. PV voltage is very low voltage. You can boost, you can increase the voltage by means of the boost converter. And capacitor CDC is connected to maintain a pure DC. Output of the boost converter is DC, no doubt, but there may be a slight fluctuation will be there. In order to maintain a constant DC voltage, this CDC is connected. And using the current controller technique, you can generate the PWM signals, and accordingly, the output of the inverter will be monitored. Monitored means you can get the pure sinusoidal. That is also possible with a small L filter. You can connect at the output of the inverter. Then after that, this will be connected to the utility grid. This is a basic block diagram of a PV system. And when we are talking about the inverter circuit, PV interfacing inverters, and we are producing the switching signals to turn on and off the IGBT switches. And there are two different techniques to get the PWM signals. One is the unipolar switching, another is the bipolar switching. That you can see here, the reference signal and current signal, carrier signals are compared to produce the switching signals. This is given here at the what will be the output for unipolar switching and bipolar switching. Then next is the design aspects. As I told you that when we will be thinking of a small PV system in the laboratory, how we will be designing for the research purpose. That you can see here. The design aspects means we have to think that this is a system. Then how you will design the inverter system? Means what should be the rating of the inverter, or what should be the capacitor rating? Like that, you have to design considering the load condition. Those things are written here. Design parameters, selection of grid interfacing inverters. You can say what is the voltage rating of the switches. That is written here. Similarly, you can think of DC link voltage selection. Those already these are available in the articles, and we have taken from the articles. You can go through it, how it is derived also. We will not be discussing these things, but when you are simulating anything, any system, first you design the parameters, then you go for the simulation purpose or experimental purpose. This is the DC link capacitance selection also, that is taking the ripple into consideration. The value of CDC is calculated. One example also given here to find out the value of CDC. Then different types of the PV inverters. These are also, we know that centralized inverters, string inverters, multi-string inverters. It has the advantage as well as the disadvantage. If you go for the centralized inverters, that means only one inverter system for all PV. All PV modules are connected in series, and you are going for the only one inverter, so that you can connect to the utility grid. Definitely, there will be disadvantages will be there, because when the inverter is malfunctioning, then the power supply will be completely stopped. You can say that is the major disadvantage of the centralized inverter. Similarly, the string inverters, you can say the here number of inverters are connected to the different PV modules. Then in that way, you can say the size of the inverter will be reduced and separate MPPTs will be used. These are the advantages, you can say, increases the overall efficiency. Then the multi-string inverters. Here the multi-string inverter is the further development of the string inverters, where the several strings are interfaced with their own DC to DC converters to a common DC to AC inverters. Every string can be controlled individually. Thus, the operator may start his or her own PV power plant with a few modules. Further enlargements are easily achieved since a new string with the DC to DC converters can be plugged into the existing platform. A flexible design with high efficiency is hereby achieved. This is the multi-string inverters. The next section, as I told you, we'll be discussing a few things here. Power quality improvement. Why the power quality improvement is essential? As I told you, that if you means you just remember the inverter operation, inverter output generally it gives the square wave, means voltage waveform, or you can say the rectangular waveform. That is not a pure sinusoidal. But we need the pure sinusoidal output voltage at the inverter output so that you can fit to the grid or you can interface with the grid. In that way, you need the few control aspects, or you can use some filters which can eliminate the harmonics dynamically, because that rectangular voltage waveform means it is nothing but the combination of fundamental component as well as the harmonic component. We have to eliminate the harmonic components so that you will get the only pure sinusoidal or the fundamental at the output of the inverter. Here we'll be discussing few things, very basics of the power quality events, you can say, and what is its effect, and power quality problems, and what is the power quality improvement using active power filters, that we'll be discussing here. These are the basic definitions of the power quality problems. Any power problem manifested in voltage, current, or frequency deviation that result in failure or mal-operation of the customer equipment. That is the power quality problems. Here, because when we are talking about the power quality issues, definitely we are talking about the power quality issues in the microgrid system. And here the other problems are there. That is, means you can say the high impedance faults, grid synchronization. So many problems are there in the microgrid system or in the PV system, but we will be focusing here particularly the power quality issues or the harmonic elimination in the system. Then next is the power quality effects, the general classes of power quality problems. These are the problems we all of us know. Hopefully, will not take much time on this. Transients and voltage fluctuation means voltage sag, voltage swell. So many power quality events are there. Those things will not be discussing here. And these are the very basic definitions of transients, undesirable momentary deviation of the supply voltage or load current, also known as the surges or spikes. These are you can see that how the transients occurs. Then the short duration voltage variation, that is here. Means you can say that interruption, sag, and swells. There are depending on the magnitude and duration, you can segregate all these different types of the voltage sag and swell and interruptions. Then we are talking about this DC offset, that is the presence of a DC voltage or current in an AC system. That is also unwanted signal that also we have to eliminate. Can result in corrosion of network and customers' earthing systems. And the important part is ours is the harmonics. As I told you, the harmonics are you can say the because of the operation of the inverter, or the inverter output itself contains the harmonics, or you can say that depending on the load connection, that also generate the harmonics. If the nonlinear loads are connected, that will also produce the harmonics into the system. There are different aspects of the harmonics, and we have to eliminate those harmonics. And these are the parameters to determine how much harmonics present in your output voltage or output current, that you can determine by means of the THD and displacement power factor. All those. These are the parameters used how the inverter, how means how best designed of the inverters used for the microgrid system. And as I told you, the power quality improvement, it is only possible by using the different types of the filters. And here the passive filters and active filters will be there, as well as the hybrid power filters. Passive filters, all of us know this is bulky in nature, and it will eliminate a particular harmonics. In that way, we are going for the active power filter, which is you can say the dynamic in nature. It can eliminate the harmonics, total harmonics present in the system. That is possible by suitably designing the active power filter with the control circuit. And these are the configurations of the different types of the passive power filters. And here you can say the active power filters and the hybrid. Hybrid means combination of active power filter as well as passive power filters. And here we are giving a small example of a sound active power filter. Let your source is connected with a load, nonlinear load, and definitely the source voltage is sinusoidal. Source voltage is sinusoidal, but what it is drawing, the current, it is a nonlinear current because the load demand depends on the load demand. Then as the nonlinear load is connected, then it is drawing the nonlinear current. It contains both fundamental as well as the harmonic components. But our main desire is it should draw the sinusoidal current from the sinusoidal voltage source. Then only we can say we are operating the system at unity power factor, or we are drawing the power with the unit power factor. This is a configuration, you can say, that sound active power filter, and there is a nonlinear load connected, that is a rectifier based load, which is treated as a nonlinear load. And here the job is active power filter to compensate the harmonics. That means you have to produce the current by means of active power filter, which is in phase opposition of the harmonic components. That is the main role of this active power filter. And this is only possible to get the feedback signals, what is the load current contains, means how much harmonic component is there. And once we calculate the harmonic component available in the load side, then that current can be produced by the means of the active power filter, which will be means in opposition to the harmonic component, so that both will be cancel each other, and only the source current will be the sinusoidal current. This is the design aspect modeling of the three-phase sound active power filter. This is the dynamic equations of the APF that is given here. We will not be discussing the mathematical equation. It is very much clearly written. Sorry. I pressed somewhere else. We are discussing here only. Yes, Kamana sir. Hello.
Yes, sir.
Audible? Okay, because
Yes, sir.
otherwise I will think that I am talking alone only.
No, no, sir. It's audible only. No.
Okay, fine. And this is a current control loop and voltage control loop. How to generate the PWM signals by taking the feedback signals from the load side, that is given with the block diagram here, so that you can generate the compensating currents. Always we calculate in D axis and Q axis so that the complexity will be reduced, and we will go for the active power component and as well as the reactive power component separately. Instead of designing the control circuit in the ABC frame, we go for the PQ frame. This one you can see here a few results already. It is published. We can say here that different conditions we have taken, how the active power filter is working. And if you'll see here, the source voltage is almost sinusoidal because, as I told you, that source voltage we are not distorting at all. And only the load current or the source current is distorted because of the load nature. And load nature is nonlinear, and it will definitely draw the nonlinear load current that you can see at the initial part of the load current. That time, active power filter is not connected. Okay. And when the active power filter is connected, after that you will find that load current, no, that source current, it is coming almost sinusoidal, you can say, because it produces the compensating currents. This APF current is a compensating current, which eliminates the harmonics. You can see here that without active power filter, what is the THD? And once you connect the active power filter, it is drastically reduced. Okay, because without active power filter, it was around 25.27%, and now it is coming around 5.4%. And different load conditions also we have taken. The load variation is there, and you can increase the load side, means increase or decrease the loads. And under that situation, whether your active power filter is working perfectly or not, that we have verified. That is also working satisfactorily, you can see. Here also we have taken the unbalanced load, because three-phase load we have connected. Means you can go for the different types of the load conditions, like the unbalanced load also. There also we have checked that active power filter is working satisfactorily. This is the unbalanced load, all those things we have discussed. Now we will come to one of the system configuration. This is also a published work, PV integrated SAPF. Here you see that source is connected with the nonlinear load, and we are controlling by means of the PV inverter, you can say, and so that you can maintain the current drawn from this source is sinusoidal. That is possible. Here the design aspects are given for a two-stage PV SAPF system. This is already article is there, published article. You can check also what are the assumptions taken for the designing of the capacitor value. All these design aspects are written here. And here we have tested it in the laboratory scale, that how it is operating with the different irradiation. Means we have taken the different irradiation condition also. We have checked that MPPT is tracking the MPPT. Calculated value is around 303, I think. It's coming almost in the practical case also 300 watt. That kind of result we have obtained using the PV SAPF system. This is also a few results that you can check that how the harmonics is reduced without active power filter. PV assisted active power filter, it is 26.58, and with the PV assisted active power filter, it is 2.652. And here the control technique is we have taken, I think, Kalman filter based MPPT, and control technique something else I have not remembered here exactly. Now we'll come to the last part of the control and energy management in AC DC microgrid system. As I told you that when we are talking about the microgrid operation, particularly we can operate either in grid connected mode or in islanded mode, or you can say the seamless transition. That means from off-grid to on-grid, on-grid to off-grid, like that. But there are major issues are there also that most of the research also focused in that particular area, because when you will be going from the for a seamless transition, you have to see that what are the different issues are possible. Because if we say one of the example that it is a complex microgrid network, and because when we are working in a research laboratory, we are thinking that load is within our control. But in a complex market system, we can see that if it is a market system and let it is suddenly the grid was connected and it is uh, let the grid is isolated from the microgrid. In that case, how the power will be managed? There may be a sensitive loads will be there, and maybe that what is the PV generation or wind generation that is not sufficient to meet the load demand. In that case, the battery may be used. That is one of the option. By using the battery, there is also a chance that it may not meet the load demand. In that case, also you have to see that how you can curtail the load, means which loads can be disconnected from the microgrid. Because once it is coming to the grid operation, you have to think. These are the means major issues are there. Similarly, the islanding detection is also another major issue. That how quickly you can means detect that the grid is isolated, and accordingly the control technique will be changed. Control technique means when the grid is connected, you can say that inverter is controlled with the current control mode. And when the grid is isolated from the microgrid, you have to operate the inverter in the voltage control mode because you have to maintain the voltage and frequency particularly. Here one of the system we have shown you that generalized structure of a microgrid. This is also one of the published article. And what we are talking about operational requirements in grid connected mode to islanded mode. Due to the grid failure, or you can say that intentional disconnection or other causes, system will shift from the grid connected mode to the islanded mode. Under that situation, you have to go for the fast islanding detection scheme. It is necessary to protect the DG system. For stable operation and continuous power supply, subsequent to isolate to the islanding detection, a seamless transition is important. In such case, the DG interfacing inverter should switch from the current control mode to the voltage control mode quickly. Because when the grid is available with the microgrid, we are not bothering much because it is automatically voltage and frequency is maintained by the grid itself. But when it is isolated, then the means problem is that how to maintain a particular voltage and frequency. That you have to go for the optimal power management or how you'll maintain the both the sides power also, means the load demand as well as the generation of the power. And when you are going for the upgrade to on-grid system, then grid synchronization also very much important that time. All those aspects are written here. Means, what are the research challenges and how the people are working. In grid connected mode, the output voltage and frequency of the microgrid are primarily detected by the utility grid. The inverters acts as a current control source to feed the available power. The inverter should maintain the DC link voltage at nominal or stable operation of DG system. In case of islanded mode, the inverters acts as a voltage control source to maintain the DG system voltage profile. The controller of the DG inverters would have control over the current dynamics. The controller uses voltage compensators to generate the current references for current regulation. Here, the schematic picture is given for the grid connected mode and islanded mode. Sometimes we are operating with the different DGs. Let the multi-DG system is there. And the multi-DG, you can say the multi-DG microgrid system. Then when it is islanded, you can say that one of the DGs should be operated in the voltage control and the other DGs will be connected in the current control. Here it is shown only with the single DG. Here the flowchart is given, how the grid synchronization control load setting algorithm, and these are the requirements will be there. Means when you are going for the seamless transition of the microgrid system, that how quickly you can detect the islanding situation, and when the microgrid is on grid system or off grid system, depending on that, you have to go for the load setting algorithm or grid synchronization. If you'll be going from the upgrade to on grid, you have to go for immediately for the grid synchronization. Those things are written here. And this is a one of the experimental setup in the laboratory that you can see. Our papers are published. Anyone is interested, you can go through it. Few results are there. These are the simulation results that under different scenarios, islanding mode, grid connected mode, those things we have discussed here, and we have shown you the results. Means how the current and frequency it is affected, all those things. Voltage is also shown under islanding condition as well as the grid connected. So this is the few results. The next is coming to the, as we told you at the beginning, that DC microgrid. This is also published in one of the industrial informatics, that taking the different sources as well as the energy storages. As I told you, we will be taking the fuel cell as the energy storage along with the battery, supercapacitor, and PV. That thing we have taken, and how the power is managed and controlled, the DC link voltage, that we have published here. That you can see, this is the our general light diagram. Here you see that PV system is there, battery bank is there, and also the supercapacitor and fuel cell is also there. And we are mainly connecting the DC loads to the DC grid, you can say. And here the AC loads you can connect, but by means of the DC to AC inverters, that is possible. If you want to operate the induction motor or anything, that you can connect via the inverters. But here we have taken the different scenarios and how the means power or how the voltage is maintained at the DC side. That is the main challenge here, and how you can manage the optimally power. And we have to see that charging, discharging rate, and it should be limited within that. All those parameters we have taken into account, and the work is published. This is a fuel cell only, a fuel cell based DC microgrid, and it is also tested by making the controller by means of the Xilinx. That also we have checked the results. This is the fuel cell plus supercapacitor. That also we have tested with the DC grid. This is the control algorithm is generated using the Xilinx. That we have tested. That time the hardware was not there with us. That we have done the HIL simulation. These are the results. You can see how the load power and fuel cell supercapacitor, how quickly these are the functioning that you can check. And here it is a standalone self-reliant DC system. Here also the same thing, but we are connecting a PV system here along with the fuel cell and the battery. And this is the control scheme of a standalone DC system. Now I'm continuing with the lecture. Registration of ATAL students for competition. Okay. We wanted to know students have registered. I sent an email to Meda. Then Meda saying in the email, just remember the other day I spoke to him, she saying that other the details can be taken from Banjai because the ownership has
anyone's approval or knowledge, the registration link is been created at the computer center. How can they transfer ownership to academic office? And when we are asking for the list, she's saying, please take from Banchai. Banchai has no knowledge about that thing. And all these years it is
Okay,
being
we'll
handled.
discuss more. Yeah. Okay, sorry for interruption.
So it's okay, Professor. Please.
Mm, Okay, this is the power management system. We have taken the SOC limit also, minimum and maximum limit. And with the different conditions, we have checked how it is operating satisfactorily. That you can see here, the few results we have published, we have cited here, but many more results we have given in the paper. Here you can see the particularly the how the super capacitor means how quickly it is coming and in the operation, that you can say under the dynamic load change, the super capacitor will come fast, and because the time taken by the battery, it will be more than the super capacitor time constant, you can say. In that way, the different operations are here: fuel cell, super capacitor, battery, all those things. And here we have taken the hydrogen fuel cell, and accordingly we have checked how it is working also. All those things there. Grid. This is a grid-tied self-reliant DC system. Before we have told you that it is a standalone system, but now it is a DC system is connected to the utility grid by means of the inverter. Here also the algorithm is written in written means it is shown with a block diagram. That is how the power management and control scheme is operating. That time also we have used that same as I told you, the Xilinx and platform, and we have got some results, HIL results, and that was included at the beginning. This is all about as I told you at the beginning, we'll be discussing the three aspects. One is the basic ideas of the microgrid system. Then we discussed about the power quality improvement using different power filters. Particularly, we have shown you one of the sound active power filter, and how the means harmonic elimination is possible, and how much harmonics is reduced. And the third aspect, we told you about the different microgrid system. Either it may be AC microgrid or DC microgrid, but you can operate either in standalone mode as well as in the grid connected mode. But the power management, islanding detection, and load shedding algorithm, so many means when we will go for the multi-DG and microgrid, complex microgrid system, we have to think different aspects also. Means how means sometimes the PV may not be operated in MPPT mode. It may, depending on the power requirement, only the power will come from the PV. Those things are to be focused more. And here we'll be talking about a little bit about the few research articles what we have already published or presently we are working also. This is one of the work we have already published in the industrial application. Uh, this is the loss of utility detection and seamless operation of a distributed generation system. This is the islanding detection as well as the control for a seamless operation of the DG system. Here, this islanding detection and seamless transition, it is already shown the results. Then we are not discussing much here, but we will be coming here. Here, one of the article which is at the beginning I told you, one of our research scholar, he is working on reduced switch multi-level inverter with different control techniques. Different control techniques for improving the power quality. He has published few articles, maybe around 6-7 IEEE papers, particularly in this reduced switch multi-level inverters, designing the different topology and the control schemes, how the power quality can be. Here, one of the paper is the selective harmonic elimination, because you can reduce the selective harmonics, particularly the low order harmonics. That is easy for a control scheme, you can say, and that way it is used selective harmonic elimination. Here, the uh, concept is given with the different equations. It will do the output voltage equation because it is a Fourier series, and definitely the fundamental component and third harmonic, fifth harmonic, all those components will be there. And here main focus is to reduce the low order harmonics by designing the selective harmonic control. This is the hardware sketch, you can see, and with a multi-level inverter, the different modulation index is taken also for testing purpose, as well as the load change, frequency change, all those things are tested and the results are shown here. What is the THD contents? You can see it is drastically reduced, means around 0.95, 0.6, which is all, means you can say the pure sinusoidal kind of thing. Then here also one of the publication is there, that is same type of active power filter, how the power quality can be improved. Mm. Will not be discussing much here because participants, those who are interested, they can see the our articles, and if they have any kind of issue, also they can interact with us. We can provide the support wherever possible. As I told you, my presentation almost going to be completed here. We have discussed few things. Means first part, as I told you, the basics. Then the second part, we told about the power quality improvement or harmonic elimination using active power filter. And third one is the seamless transition, or the, you can say, the grid connected mode operation of microgrid or off-grid operation of the microgrid by means developing those islanding detection, fast islanding detection, or you can say the advanced control strategy. You can go for the synchronization technique also. All those things are there. So we have discussed, and few research articles are here. You can see.